So last time I at the end of the last class I alluded to uh, some kind of thing that we want to prove about data compression. Uh, but I believe the whole statement and the proof of the asymptotic equipartition properties probably not in Nielsen and Chuang. So I uploaded my notes, my handwritten notes on the course website this morning. If you want to look. There's also a book, a great book by David McKay. Free ebook. What's this called? Information theory, inference, and learning algorithm information. Theory, inference, and learning algorithms that talk about this. อันนี้เริ่มแล้ว Okay. So as I mentioned about homework last time, it will be due on next Tuesday. And if you have any question, yeah, feel free to ask me. And of course, since we have the Discord server, you can also ask questions on the Discord server as well if you're not here. Yeah. I mean, usually I'm not here too, so yeah. Okay, so just a bit of a reminder. So last time we talked about various entropic quantities that's defined based on Shannon entropy, right? And a lot of relation between them that we can sum up in this kind of a Venn diagram for two random variables. Right. For example, we have the conditional entropy, which is the information that you can learn about X, given that you already know about Y. And so it's sort of, well, according to this Venn diagram and the definition, and this also it make intuitive sense that is the information of the joint random variables, but then you subtract the information of Y that you already learned. And so it's represented by this crescent area, or the mutual information, which I denote like this. And this is the part of the information that is shared by X and Y. If the random variables are correlated, if they're not correlated, i.e. independent, then it's 0. Okay. Okay. So today, I think we mainly talk about the AEP, or the asymptotic equipartition property, but it's kind of hard to say. Maybe I should say, talk about a type of data compressions idea that is based on Shannon entropy. And so the setting is the same, but I'm just, for convenience, I just make up a new name for things. So again, we have n IID random variables. So this is capital N, and by IID, right, it means that all of them are distributed according to the same distribution, which we call X, like the random variable X, which takes the values. So again, this is the same thing that we have been talking about, right? It's the same as throwing a d-sided die n times, independent throws. And so after we throw it n times, we have a length n sequence of some values, and then each value of the x is like from 1 to d, right? For example, so you have some string, and so I name the sample space of all sequences of length n like this, just for simplicity. And what we have shown before, that in the limit n going to infinity, all of the probability in this space is concentrated on the typical set. So you remember the definition of the typical set? Yeah, the frequency that each symbol appears is equal to its expectation value. And so the picture is like this, right? That I have a big space of sequence xn. So for example, if let's say d is 2, so it's really, this is the space of bit strings, and n is 10, for example, so length 10. So this, the size of this space is 1024, right? 2 to the 10. And then let's say the Shannon entropy says like 0.7. So we have proved, right, that the probability of sequence appearing, so let's say, or the number of typical sequence. Let's do this because I want to draw some blob in here, right? Okay. So let me denote the typical set, by this. So we have shown, right, that the size of this is 2 to the nh. And so how do we, how can we visualize, how would we visualize the typical set in this case? Yeah, so let's say if h is 0.7, then the size of the typical set would be 2 to the 7, right? Which is 128, I believe, or something like 110. And then we know that the in the infinite n limit, all of the probability is contained in the typical set. So we only, if say I want to encode a message that send this sequence of symbols, these strings, then I only have, in the large n limit, I only have to care about strings in this set, which could be much smaller than the whole thing. Well, of course, here I put n equals 10, so it's not n, it's really far from n going to infinity, but yeah, it is just an example. And that's why we're gonna do what we're gonna do today, right? Is to actually analyze the what happens when n is actually finite. Right? Okay. So for that reason, I am gonna define an epsilon typical sequence. if this quantity, so it's like the so it's like the log of probability per bit is close to the Shannon entropy of the source. So this is the same if you take out the absolute value, right? And take the exponential, then this is the same as the probability of each sequence happening is bounded by something close to 2 to the minus nh, but we allow some error epsilon. And then moreover, the I will call the set of epsilon typical sequence all by tau with parameters n and e and epsilon. Okay, so this is just a definition, right? But now we want to be able to say what is the, so now if I have like the sample space of all sequences, right, and n is some finite value, not infinity, then we want to sort of control how much probability is really in this typical set, which would depend on epsilon, for example. So in other words, we would want to prove some theorem related to the probability that this event is true, right? That this thing is that any sequence that I pick would have the empirical entropy close to the source entropy. And so we can sort of already see the way that we would proceed is by something like applying the law of large number. Okay, so let us prepare ourselves by calculating things like variance that we need to use for a law of large number. So in this case, the sample mean will be played by the role of this quantity, right? Sample mean denoted by S sub n. And since the let's do it like this. Since so this is the joint probability, right? So it's the probability of the sequence is a joint probability of each symbol occurring, and since we are already assume independence, it splits into product of probability. Right? But the probability is split into the product, so the log split into sum, and then I would just pull the minus sign in here. And this is nothing but surprisal, right? And k here denotes the trial. Right? So I put j sub k in here, but usually since their IID anyway is all the same random variable, so a lot of time I just ignore the k and just let's say that, oh, I have a random variable j. And so the the mean of this, so it's like the expectation of the expectation value of the sample mean is just the same as the theoretical mean, which is the Shannon entropy. For the variance, square first and then takes the expectation value. So if it would be a little bit ugly if you try to calculate directly, but we can recall that we already proved some time ago that this is 1 over n times the variance of whatever variable, random variable is in here. So in this case, the variance of j. And so now I can plug this in. So let's say, so the variance is the deviation random variables square. Okay, I have to make sure. So it's the, okay, how many brackets I have? Deviation square, and then take the expectation value, which and this this expectation value is the same as the second moment minus the square of the first moment, right? And so now I will use this notation as sum over x of probability of x, and then I have oh, sorry, I said that formula, but we don't have to use it here. I just plug in the square of this directly, and then I have this, and I have this. Okay. Okay, so this is something, but to get simpler, we can do some kind of bound. For example, the entropy here is bounded by log d, right? From last lecture. Let's go over there. Right. So that thing, it has negative sign, but in the end you square it, so it doesn't really matter. So say if I consider this quantity, well, log p is negative, right? Because p is less than 1. So if I ignore it, right, then I just get the entropy, and then this thing we know that is log d. So it's probably not a very great bound, but why I'm using this is just because this is independent of n. So at least it's fine. So because we just want to look at the behavior of this probability as n gets larger. And so I can say that the variance of j is less than log d squared. And so this guy is less than this. Yeah. Okay, so that's yeah, there's a sufficient preparation. So now I'm gonna state what we actually want to prove, which is a bit long. So let's see. Maybe I'll use half this board and maybe try to prove it in here, and then when I prove some part and I erase this, and then I use this part again. Let's see. Okay. So I will divide this into 3 parts. Okay, so first, so if you are used to statement in like mathematical analysis, yeah, I think you won't have any problem with this kind of thing. But if not, you might have to go back like after class and then think through the statement carefully about what it means. So for example, here for any positive value of epsilon and delta, there exists a threshold and not such that, okay, for all n greater than n naught, the probability that let's see, sequence is in, so maybe for sequence I just erase the comma sign just to mean that a sequence is a concatenation of each symbols, right? And then say that this is in the, it's not epsilon, right? It's in. The probability that a sequence is in a typical set is greater than 1 minus delta. Yeah, so this is the infamous epsilon delta statement in hardcore calculus. To the number of typical sequence, number of epsilon typical sequences satisfy the following inequality. And then on this side is almost the same, except that it has 1 minus delta here. I will discuss the significance of each part in a minute. And the third one is, so let's say let R be any set of sequence of length n. Such that R is okay, so let's say the size of this set is 2 to the n times R, where R is bounded away from the Shannon entropy. So this is a strict inequality. Then for, again, a kind of this statement, for any positive value of delta, there exists and not such that for all n greater than n naught, the, oh god, I cannot like move this a bit. The sum of basically the probability of this set R, which is simply the sum of the probability of all sequences in that set, right? It's less than this. Okay. Yeah, so let's, I guess, first think about what we are trying to prove here. So the first part is, yeah, I think it's quite easy to see the meaning, right? That this is saying that once you so basically, if I have like a typical set for some value of n, and I so we know that in the limit of n going to infinity, then the epsilon would not really matter, right? So basically, all the probability would just come into this set. But then, so let's see that. But what this statement means is that, say, if I have specified some value of epsilon and delta, then the epsilon and delta would determine the value of the threshold number of trials in naught, such that once n get past n naught, then the probability of every other sequences that are not in the typical set would just be delta. And this is true for any positive number delta, so we can suppress it as low as close to zero as we want, so that all of the probability sort of just lies inside here. And then the second part of the theorem is just talk about the size of this. So it's a bit of a generalization of the statement that we have proved before, but with epsilon. So the third one is interesting. So this is saying that if you pick any set of sequence here, well, maybe I should draw R to be a little smaller in this. So the motivation for the third part of the theorem is that, well, as we already discussed, the idea of this idea lead to data compressions in the sense that when n is large, I can just encode the sequences in the typical set, right, and then ignore other things. But we can ask the question, well, is there a smaller set, some set that's smaller than typical set that would just compress the file compress the data just as well as the typical set? Because if it exists, then we should use that set instead, right? Because it's a smaller set, and so it compresses more. But this part of the theorem says that if we have a smaller set, there will always be some number of n that once n get past that, then the probability of this set is simply like close to zero. In other words, if we use any set smaller than the typical set to compress the data, then once n get large, it will all be error. So all the probability will just go away from the set, and we cannot really use it to send anything without error. There'll just be error basically. Okay, is there any question or comment about this before we really prove it?
What is the thing?
Oh, sorry. Yeah, because when I write on the blackboard, it's hard to distinguish between calligraphic and the normal font, right? So yeah, let's do this. So and then this R is just a constant. Yeah.
Then why don't we just, because R is less than Hx, right?
Mm-hmm.
Why don't we just put X then change the cell sign?
Yeah, it's true, but it's just one more constant that I can write in the proof. So another yeah, it's just for convenience. Some other authors would not define R, but they would define the difference between H and R and then use that in the proof. But yeah, just notational. Yeah. All right. Okay. Okay. So the first statement is really just the law of large number, right? So recall, let's see. So typically the law of large number would be something like, so the way we wrote it before, something like this, right? And then I have the variance here and something there. But what we want here is an inequality in the other direction. But it's easy because then the right hand side would just be 1 minus the variance over n epsilon square. And so if I put the random variable j in here, the surprisal, log p, then that's basically it, right? And then this is greater than 1 minus the variant of j over this. But then we already have a bound on the variance of j, which is log d square. So it's an upper bound, but since there's a minus sign here, it's a lower bound of this thing. So I just use the blackboard magic and then replace this with log d square. The important point here again is that in the end, I really don't care about this constant. It's just that it's independent of n. And so if I notice that this is the value delta, then that's the proof of the first statement. So the first part, okay. Oh, but if you want to use the theorem, right, you would, the direction you would go is that you would specify the epsilon and delta first, and then you can calculate n naught from here. Okay. So for example, if say d equals 2, so it's just a Bernoulli trial of like tossing coins. And then if I want the probability of the epsilon typical set to be something like this. This is 0.999, which means that the delta is 10 to the minus 4. And then let's say if I want epsilon, which is in the definition of the typical set, to be something like maybe 10 to the minus 4 as well. So this is the error. Okay. And then you just plug in here, invert the put n in the denominator, in the numerator, and then you guess that n naught is 10 to the 12th. And so the epsilon and delta will determine what at which value of n that we could say is large n. Large enough n for this choice of epsilon and delta. Right? Okay. So for part 2, we have to let's separately prove the upper bound and the lower bound. Well, so for the upper bound, so I will just write, because I'm too lazy to write the whole sum, or like the whole symbol, so I just say it's the sum of our typical sequence here. Of course, a trivial upper bound is 1. But then this is related to the number, to the size of the typical sequence as follows, right? That the sum is, if I want the lower bound, then I can pick the minimum probability in here. So min, and then just multiply this by the size. But we already know the minimum probability from the definition of the epsilon typical sequence. And this is 2. This is with epsilon. Yeah. So now we get an upper bound on the size of the typical set. I just have to move this to the other side. And that's it. Okay. Okay, so for the lower bound again, so I write the sum of the probability of the sequences in the typical set here. Well, what would be the lower bound here? No, if you use max p, then it's this side, right? Yeah. Yes. Yeah. This is what we know, right? Because, well, from the first part here. Yeah. Because basically, yeah, typical sequences take almost all the probability in the space, and by almost all we say is 1 minus some sort of small number delta here. Yeah, but thank you. Yeah, so this is already on the right part, because now we know that this is bound by, well, this is just that, right? And therefore, I move this to the other side again. Right. This is 1. Okay, I didn't get the side wrong there. This is good. Yeah. All right. Time is right now. Okay. So for the third part, oh, sorry, I say I'm not gonna erase this. Okay. Yeah, because probably I want to keep the statement of the theorem here. Right. So is it okay if I erase this side? Okay. Three. Right. So now so what we want to bound is the sum of probability of sequences in R, in Rn, right? Right. And we'll do that by first splitting the sum into, so let's say Rn may or may not have overlap with the typical set. But then I can split the property here into the sum of the thing of sequences inside the typical sequence, the typical set, and then those outside, which I would say atypical. And we want this to be less than delta, right? And well, so this probability we can bound the same way as what team's answer over there, which I already erased, because we know that the probability of sequences outside of the typical set is something like delta, right? But the value of delta, we are free to set the value of delta to anything, right? It's just any positive number. And so by in the usual fashion of mathematical analysis proof, I will just set this to delta over 2. Just so that after that I will bound this by delta over 2 as well, to have the delta at the end. Yeah, this is very usual in like analysis proof. You just you bound each term by something that looks like a weird number at first, but you just want the final number to look clean. Okay, so how do we do this? So just for to prevent confusion, so this is just some value of delta, right? Which I call it delta prime. And so here I just mean that there is some value n not prime correspond to delta prime. So if I write this out, it would just be this, right? This value when n is larger than this, then I have this bound. So now what about this bound? I want to give an upper bound, so you just do the same thing. So I bound it in terms of the max because it's in the typical set, right? So we can use the property of typical set or typical sequences to bound this as well, like in the proof of the second part. So I can do the same, use the max p, and then I have the number, the size of the set here. So if I write it out, but the form of this doesn't really matter. The only thing that matters is that this is independent of n, right? Therefore, there is some value of n greater than n naught prime, and the condition greater than n naught prime here doesn't really have anything to do with this part, right? It has to do with this part, that we want to bound both of this at the same time. So whatever n I choose here is better be larger than this too. But here, yeah, we don't really care about this value here. It's just that you can suppress this probability as low as you want, right? Because just by increasing n. So there exists such that this term is less than delta over 2. And so therefore, for such number n, capital N, then this whole thing, the sum of this is really bounded by some positive number delta. Right. So any questions up to this point? Yeah, because it's like the most mathematically involved part of the what little we're gonna talk about classical information theory. So then now, since we are done with that, now let's make it. I want to give a more rigorous statement about data compression using this idea. In particular, for the sequence of random variable, which now I call x to the n, so which I already erased, it was somewhere here. So let me define a code first. So lossy in epsilon block code, and this is and the block here is just there to imply that we are gonna encode these symbols together as a block of length n, right? A block code is a set. For example, a typical set, but it doesn't have to be. So in this general definition, so some set S, yeah, maybe it's more correct to say to just put the usual thing here, just random variable x1 to xn, and I just denote this to be the sample space of all sequences from these IID random variables. Such that the probability of a string being in this set is close to 1. Oh, sorry. Yeah, now we just have one variable, so I guess you can give it any name you like. If we are already used to delta, then I would change this to m delta. Yeah. Yeah, but is it clear to you that why we're using this sort of why we're defining code as a subset? Okay. That is the same idea, right? That because we're just gonna encode and decode sequences in this set only, and then the delta is just the loss part here. You actually lost information when n is not actually infinite, but if you can compress it as close to 0 as you want, then you don't really care. And then moreover, I would define the rate of a code as the log of the size of S divided by the number of symbols. So it's kind of like the so remember that this is log base 2, right? So we are measuring, basically this is bit per symbol. And by symbol here, I mean the number of IID random variables. So if you don't compress anything and just use the whole set, then the numerator is just n, right? So you basically encode 1 bit of information by using 1 bit. But we can sort of already guess where this is going. So if you use a typical set, so the thing over here would just be n times the entropy, right? And then the n cancel, and so it says that you can go, you can compress 1 symbol to possibly less than 1 bit, because the max of entropy in log base 2 is just, well, if your information, if your random variable, let's say just for simplicity, if x random variable x is already binary, so it just like has d equals 2, and you use a typical set, then let's say d equals 2, and then I use the typical set. If I just ignore x epsilon, this would be this would be just the entropy, which is less than 1, right? Yeah, so if you know the entropy of the source, you can compress the amount of message you have to send. And actually, the what Shannon proved is that this is the best that you can do. It's called Shannon source coding theorem. Which state that the minimum possible asymptotic rate, minimum possible asymptotic, meaning that n going to infinity is the entropy of the source. So inverse and n IID random variables can be compressed into n's time hx, h of x bits with negligible loss. And conversely, if they are compressed into a set that is smaller than, if you are compressed into fewer than n times the entropy bits, then it's certain with probably 1 in the asymptotic limit that all information will be lost. That's kind of the give the limit of the best thing that you can do in terms of data compression like this. And yeah, hopefully if we don't run out of time, then we'll see a quantum version of this at the end of the course. So this basically gives the meaning of the Shannon entropy as the number of, so we are using base 2 here, right? So it's the number of bits that I can compress the random variable into, which doesn't have to be an integer. So let's say if I if n is not infinity, if I really want to say like how many bits that I can encode into, I would not write I would not write this, right? Because it's not an integer. Maybe I put the ceiling here. So it doesn't have to be an integer, and it just means like whatever the number of bits of information that you can compress your source into, which is a more I would say a deeper version of when people saying a bit is just something that can have value 1 or 0, and by extension you also hear that a qubit is something that have value 1 and 0 and like all superposition of them. But yeah, at the end of this class, we also learn about quantum entropy, which also has the units of, yeah, it has to be unit of qubit, and the entropy, and that entropy would also doesn't have to be an integer, and it just means the amount of content in the quantum system. So basically, it would be something like the dimension of the Hilbert space, or the minimum dimension of the Hilbert space that you can compress your quantum state. Okay. All right. Yeah, so next I'm gonna just like jump completely to linear algebra. So anything that you want to ask or comment here on this part, or your homework or whatever. Yeah, and people in the back feel free to ask anything too.
You say H is number of bits, right?
Mm-hmm.
So if we look at this, it's just only not more than one, or we must, for example, if I want to send this thing range n, right?
Yeah.
Should be.
It should go as n. So here, This would be the number of bits to encode just one symbol, one instance of the random variables. Yeah. Yeah, so this whole thing, if you want to send, then you can say that this whole thing is the entropy of the joint entropy of this, which would just be the sum of each entropy. Well, it's just by the IID assumption, this is just the entropy of the source times n. Right? Yeah. But yeah, you are right that because of this ratio, so unless your random variable is the distribution of your random variable is truly uniform, you can always compress it. Yeah, because this is only one when the random variable is uniform.
So the first, at first, if you want to something like want to contain, we first thing we must find the typical sequence. We first find the typical sequence.
Yeah. Yeah, and then you would just assign some sequence to some symbol, some sequence to each element of the typical set, and then actually send that in a communication. Oh yeah, maybe I can say something about a bigger picture here. Why is it called source coding? So it just needs some space. So in a communication, you can sort of abstract away all the element into these three things, right? That you have the source of information, and then you maybe encode information in some messages, some symbol, and then it goes through a communication channel, and then the receiver has to decode it. So here we are only talk about source encoding here. Yeah, so it's only this part of the diagram. We are just trying to assign a message to each sequence or each assign a symbol to each message that we want to send, and this is what we send out. What we
assign some symbol only on the typical symbol.
Yeah, so if you use this block encoding scheme, yeah.
What if I want to send some message that I don't get what is the source of it?
The source would be the ensemble. So you would have so let's say you want to send some English text, right? You have a set of 26 letters, and then you have a probability distribution over that, which maybe you get from like a frequency analysis of text. So for example, like some vowel like A, E, I, O, U would usually appear more frequently than other symbols, and so you assign like higher probability to them. Yeah. Yeah. So I think the only thing that's so the set of alphabet is something that we can agree on, is kind of like some fact, right? It's just a fact of English language. But then the thing that people have to work out is what would be what probability distribution should I assign to each letter. But once you have that, now you can you can calculate the entropy, find the typical set, and then assign some kind of symbol for each letter, for each alphabet, and then send those. Right. So here's just a source coding. A much bigger problem is on the channel, because this is where like the noise or attacker, like eavesdropper, would just go to this part, and we haven't really talked about that at all. And this is the topic of error correction. So so suppose the channel is just identity, there's no noise, there's no nothing, then whatever rule that you need to do to decode the message, you can just agree with the receiver, right? And then the receiver just get the message and decode it. But then if there is a noise here, or some malicious party trying to get your information here, then something this will mess with your messages, and then you have to design some kind of code that has error correction property. Right. Yeah, anyway, that would be error correction would be the topic of the next semester. If you want to see a preview, then one อะไรนะอาสาฬหบูชากับเข้าพรรษา There'll be a quantum IF school on error correction, quantum error correction. All right, so yeah, and please feel free to like ask me questions outside the classroom or so, or whatever. Right, so I think we're leaving the land of information theory and go to the land of linear algebra. So I'm pretty sure that all of you are already very familiar, master the Dirac notation, right? It's like Dunk, you already took some equivalent of graduate quantum mechanics, right? And it's probably full of Dirac notation anyway. Yeah. Yes. Okay. So I think the goal of something like 1.5 to 2 lectures will just sort of give an advanced overview of linear algebra. Yeah, I hope it doesn't have to be like as long as many detail as for example when I gave a lecture at summer school. Okay. So I assume that all of you know about vector space and how to define vector space, for example. So I would just say that in quantum mechanics, the only, well, in finite dimensional quantum mechanics, the only ingredient that you have to have in addition to the vector space itself is the inner product. Hilbert space, sorry, which I will often denote by the scripted H, is an inner product space. And actually, yeah, for quantum mechanics, we'll almost always just say it's a complex vector space too, right? So vector space where you can take complex linear combination of vectors. So sometimes if there are more than one Hilbert space, I will use a script letter of like other letters. So for example, like X or Y as well. Maybe. So so a vector we write denoted by ket, which can be expanded in any basis. So suppose that I have a basis element, so up to the dimension of the Hilbert space, then yeah, this is what I mean by expanding a vector in the basis, right? And then suppose, let's say that I call this basis B, just to explain a bit more, maybe just to prevent confusion. When we do computation, sometimes, only sometimes, it would be convenient to use the matrix form or vector form, right? So it's like this is kind of like a geometric or coordinate-free expression of a vector. But of course, we can have the coordinate form as well. So I can write this, for example, as a vector here. So let's say the dimension is D. So it's just write up to D. But of course, these elements are not something that's unique to the vector psi, right? Because it's dependent on the basis. If you don't, if you worry that you will confuse yourself, maybe you can put like subscript of basis here. Yeah. So sometimes, if I want to be careful, I would not put an equal sign here, because both sides are actually sort of like a different representation of the same thing, right? But at some point deep into the class, it would be unavoidable to just put an equal sign everywhere. Yeah, for example, the density matrix, people use the name interchangeably with density operator, and like usually operator, yeah, matrix is a matrix, right? And operator is like the geometric way to think about matrix, but we equate them all the time. So at some point we will drop this left-right arrow thing. Right. Dropbox. Okay. Yeah, so those are the vector. Well, now I have to talk about inner product. And I believe that now at this point, some of you should be able to recite the three properties of inner product, right? Yeah, which one I want to do first? So maybe is so let's say I would say inner product. So an inner product is a function of, so it's a way to map two vectors, so like Cartesian product of two of elements of this vector space with itself to the field. And so here, if I specify this to be complex already, then if just go to C. And so I would denote this by, say, if I have a vector psi and phi, I would just denote this just for this class to be this bracket thing. So this is the way that people would write in a product without bracket notation. Yeah, some mathematicians like the bracket notation so much that they would write like this, but and then some physics notes would even like put something like this, but I think it's overkill. So all of the properties would be almost the property that you remember for the dot product, except that when you're in complex vector space, then you just have to make up some definition that's compatible with complex conjugate, and that's the only thing that you have to deal with. So for example, the inner product is linear, but only in one argument. So here I would just put the property in the second argument because it would be a ket, and then this guy would be a bra. Right? In the second argument, so for example, if I have something like this, psi 1 plus b psi 2, then it is linear. You just put the complex coefficients. So this is in a complex scalar. There are complex scalars. And I just distribute it linearly. Well, so what about the first argument? So that would come from the second property that is sometimes called complex symmetry. Which is to say that if I swap the arguments of the inner product, well, I almost get the same thing. I just need to put a complex conjugate here. And from this and that, now you can show that another kind of sort of like twisted linearity holds in the first argument. So like then you distribute it linearly, except that the scalar in front, when you pull it out in front, you have to put complex conjugate here. Oosh. And the third one is the norm of positivity. So if we take the inner product of vector bit itself, then it should be positive. And this is the reason that we put like the complex conjugate here. But moreover, it would be zero only. This is the way that we define in a product, right? That this would be zero only if psi is the zero vector itself, with equality if and only if psi is zero. Yeah, this can be used to define a norm later. Right. Yeah, so now when we port this kind of thing into the bracket notations, so well, how does the bracket notation work? So say if I have a vector, then this is like usually we would represent it by a column vector like that. And then we sort of think of bra as a row vector. D, E, B, okay. And then bracket, or the bracket, yeah, to be sure, to be rigorous, let's say that this is come from orthonormal basis. So define matrix element by the orthonormal basis, except that since if we haven't defined the inner product yet, this bracket thing yet, we cannot define orthonormal yet. But this would be something like multiplication of the row and column, right? It's just one number. So you can, so this is kind of like a dot product, except that for dot product or inner product, you think of the two arguments, the two vectors here, as being in the same vector space. And so for example, here you would need to think of both vector as a column vector. But here we are thinking of the bra as a different kind of object. And in particular is an object that linearly map a vector to a complex number, to scalar. So like an official name of this kind of thing, like bra, linear functional, one form, dual vector, has many different names. But basically, this is a linear functions from the vector space itself. Actually, this to define this, you actually don't need an inner product, right? Because here you never really take a dot product of two complex, two column vectors. But in let's say in this general ways of thinking about it, we can define a linear combination of these linear functional, right? In the sense that if I have, so let's suppose f of psi, so suppose this is in the Hilbert space. So this is like, do I need to write this? I guess I don't need to write this. Suppose that I have a function, a linear function like this. It means that, oh, okay, I guess I don't have to write this. Yeah, suppose it's a linear functional. Then of course, linearity would mean that if I add on linear combination of vector, this would be the scalar that you get, right? And so we can sort of use this idea to define a vector space of linear functionals based on the basis. Say, for example, first you can define a basis of this new vector space based on the basis of the edge, the Hilbert space edge. Something like this, right? You can define basis element, something like fj, so that when I add fj on the basis element. So I don't know. Do you want to get here? Just to make sure. So this is basis element of the original vector space, right? We can define this to be something like the Kronecker delta, for example. And then based on that idea, I think I'm not gonna like spell out the whole like argument, but yeah, the idea is that now once you can define something like this, then you can define this to be a basis of the vector space of linear functional, and show from these properties that there is no other vector. So like if you have any linear functional, you can always expand it in this this fj. Just because if not, it means that you have something that you haven't something like if I have if there is a linear functional g outside of this set. So that means if I put any basis element here, it's 0, right? But from this, you can show that G has to be a 0 linear functional itself. So it's not sort of, well, I would say it's not a part of this new vector space, but of course it's a 0 vector in this vector space. From this idea, you can say that the linear functional form is own vector space, which is typically called the dual space, vector space, denoted by whatever the symbol for that vector space is, and you put a star in here with the same dimension. And that's just because I define the basis of this space from the basis of the original space, right? Yeah. Yeah, and so this can be done. This can always be done even if you don't have an inner product or not, because we haven't really used inner product. And so there is a saying that vector space is like a potato chip. If you have a one, then you have to have a second one, which in this case is a dual space. What time it is? Oh, it's already noon. Great. Right. So what we are gonna start from next time is that now if you already have an inner product defined beforehand, and there are many choices of inner product, right? So it's anything that defines this axiom. But anyway, in the end, we will just use the standard one, which is just, yeah. Once an inner product is defined, then you can associate this, which is kind of like, this is really a linear functional phi acting on the vector side. So it's kind of like this. But once you have an inner product, you can associate this with the inner product, and then you can go on to define the adjoint of linear operators, and from the adjoint, then you can prove theorem about when a linear operator is has an eigenvectors that form an orthonormal basis, a complete orthogonal set for a vector space, for example. And that's like the high point, the peak of linear algebra for quantum mechanics, right? Because it's called the spectral theorem, right? Because we use it all the time when we think about Hamiltonian, when we think about observable. Well, you know, observable has to have eigenvectors or eigenfunctions that spans the whole space, for example. and that come from the spectral theorem. All right, so yeah, thank you for the thing we discussed.